Hello students, in this video we'll realize the Gaussian curvature of the surface in terms of the ratio of two shrinking areas. Let's be given a surface with parameterization R of UV. Like that, okay? Then we claim the Gaussian curvature K has the form is the limit it's the limit. I had to put absolute value here because the sign gets messed up. Is the limit as delta approaches 0 of the double integral. And this, of course, this is the Gaussian curvature at a particular point. So let's be a little bit more careful about this. So I really want to say the Gaussian curvature at a point, right? So the Gaussian curvature at a point P, okay, is the limit as delta goes to 0 of the double integral of a ball centered at a point of radius delta, basically. I'll just specify what that ball is. Then nu cross nv du dv relative to the double integral over this ball, v delta ru cross r v du dv. Okay, we're here this ball. So what's the setup over here? So we have over here to parameterize our surface. So we have two-dimensional space over here. So here's R2, right? In R2, there's some open. So what we really have over here is, I'm going to suppose that point is just the origin over here, right? So there's going to be some point over here at the, let's call it the origin of radius delta, right? And the origin over here, that's just 0. This gets mapped onto what? This R2 by my parameterization R gets mapped onto a surface in three-dimensional space, right? So here's three-dimensional space, R3. So my surface looks like this. Okay, and what does R do? So R takes this ball and it moves it to some part of the surface over here, right? So it moves this, that's the image of my ball over there. So that's going to be R of this ball B delta, like that. And now, of course, every point in this part of my surface over here that we care about corresponds to a normal vector over here, right? So this could be like my n over here, my n hat was going this way over here, n hat. Over here it's going like that over there, n hat going like that over there. And what I'm going to do is I'm going to keep track of all those n hats. Those n hats are all points on the sphere, right? So in other words, those n hats are all elements of the sphere. That's my S2, the unit sphere. Okay. And so I'm going to plot all those normal vectors over here, like that, like that, like that, like that, right? And so what we have over here is we're going to have a portion of the sphere. That portion of the sphere over there, that area of the sphere corresponds to what? This area of the sphere over here corresponds to this integral over here. And then this surface area over here, this orange surface area down over here, corresponds to what? Corresponds to that surface area. And so, of course, as delta is going to 0, this surface area over here is tending to 0. This orange surface area is tending to 0 over here. That's tending to 0, right? This pink surface area is tending to 0. So this is really the orange. This is really the orange on the bottom, and then the pink on the top, right? Like so, okay? And so as delta goes to 0, as this patch tends to 0, that surface area goes to 0, that goes to 0. So we really have a 0 over 0 thing over here. And so we're realizing the curvature as, in some sense, a derivative, right, with respect to these measures being measured by these surface integrals over here, right? That's the hardest part of it, is just understanding the intuition for this over here, right? The intuition is that I take a really, really small ball centered at the origin over here, just a regular disk. that will map onto some portion of the surface over here that has a surface area. And of course, on every part of that surface area, there's a unit normal vector, right? And so I take those unit normal vectors, which lie in the unit sphere, and I figure out what portion of the unit, what area of the unit sphere they carve out, right? Now let's think about this intuitively. If you have a flat surface over here, then the normal vector is constant, right? Then the normal vector is going to be straight up, right? Which means that this numerator over here is just what? It's just a single, it's the area of a single point, which is 0. So for a flat plane, this makes perfect sense. Now what happens if there's a lot of curvature? If there's a lot of curvature, very, very high curvature, that means the normal vector is doing what? The normal vector is moving around a lot on that point of high curvature, right? Like a really, really sort of tight ball over here, right? There's a lot of curvature, which means you're sweeping up more of the sphere, right? Relative to a very, very small portion of the surface itself. So for large curvature, you have a small portion of the surface and a large portion of the sphere, which means that this is large, right? Conversely, if there's like we said for the plane, if there's not much curvature, then the numerator is 0 and the denominator is large, right? So you have these two sort of ends of the extreme. So this makes intuitive sense, at least, from this idea of like what the rough scaling has to be, right? So now, of course, we just have to do a little bit of formulation, right? And so what's the main point? So let's recall that NU hat is equal to ARU plus BRV, and NV hat over here is going to be what? It's going to be CRU plus DRV, like this. And it turns out that we've seen in previous videos of the Weingarten matrix, W is just the inverse of the first fundamental form over here. It's probably plus or minus, right? There's always this negative sign issue, right? Is this over here, and that Weingarten matrix is exactly just negative the what? Negative A, C, B, D, like that, okay? So the Weingarten matrix comes up in handy. And so now, what is NU cross NV? So NU cross NV well, RU cross RU is 0, RU cross RV is RU cross RV, so that's going to be an AD, RV. And then over here we'll have a what? We'll have an R, then over here we'll have a negative BC, so negative BC over here. Those are my RU cross RV terms, like that. Perfect. And so now what is this NU cross NV, the length of this thing over here? So in other words, the length, NU cross NV, is exactly going to be the absolute value of AD minus BC times the length of RU cross RV, and this is what's going to save the data in our analysis over here, right? And of course, AD minus BC is just the determinant of this matrix over here, which is the determinant of the Weingarten matrix, right? So this expression over here is exactly equal to the determinant of the Weingarten matrix over here, W, what? And then RU cross RV. Okay. And of course, the determinant of the Weingarten matrix is the curvature, right? So of course, up to with an absolute value over here, right? So this is the absolute value of the curvature, the Gaussian curvature, RU cross RV. Beautiful. Okay. And we know that the curvature is a continuous function, right? So kappa, the curvature, is a continuous function. So if I let epsilon be greater than 0, I can pick delta such that if we're in this ball of radius delta, k of u and v minus k of this point that corresponds to 0, 0, right? Let's see, we want u and v to be in the Euclidean space, right? So I'm parameterizing this now based on Euclidean space, right? 0, 0, of course, k 0, 0 corresponds to this k of p point over here, right? So this is exactly identically equal to kappa of p over here is less than epsilon if u squared plus v squared is less than delta, right? If you want delta squared, that works too, right? The perfect delta squared since it's a ball, right? Excellent, okay? So in other words, I know that the curvature at any point in this, the curvature of any point over here, the curvature of any point on the surface over here is arbitrarily close to the curvature of that particular point P, right? So this point 0 gets mapped to a point over here, P, which we're measuring the curvature at, right? Excellent. All right, so now the rest is just a standard analysis proof, right? So what I'm going to do over here is I'm going to look at this. So now what we can do is we can take this limit over here. So I can look at the double integral over b delta for this particular choice of delta. Now this numerator over here is exactly what? Is exactly just the the curvature, right? RU cross RV, du dv, over B delta RU cross RV, du dv. Okay, excellent. Alrighty. Good, those are genuine surface areas, right? And so now what? And so now I'm going to take this absolute value of this and going to measure how close this expression is just to k at this point P. So k of 0, 0, right? So k of 0, 0, right? Well, now what are we going to do? We're just going to fill in this expression over here. Since this is constant, I can try b over b. So this is exactly equal to what? This is exactly equal to the double integral, less than or equal to, actually. The double integral by the triangle inequality, b delta, of just absolute value k minus k of 0, 0 absolute value, RU cross RV, du dv, relative to what? The integral, double integral over the ball of RU cross RV, du dv. Okay. Now I know this expression in the numerator is less than epsilon, right? So this thing over here is less than epsilon, right? By our expression over here. And so now I just have RU cross RV over the same integral over here. So this whole expression over here is less than epsilon if what? If u squared plus d squared is less than delta squared. So I've proven that as delta, that the limit as, I've rigorously proven using epsilons and deltas, that the limit as delta goes to 0 of this ratio of the surface area portion of the sphere relative to the surface area portion on the surface itself will give you the absolute value of the curvature. Now, of course, I can make this a little more precise. I can get rid of absolute values everywhere if I'm careful with the choice of sign, right? Because I know the sign of the curvature isn't going to change either, right? So if the curvature is negative at a point, locally near that point, the curvature is going to remain negative by continuity. So I can be a little more careful over here and put like signum functions everywhere and measure where the curvature is positive and negative. But suffice to say that this is a local result. So all I have to do now is keep track of you have a positive point of curvature or a negative point of curvature of the point, and then you can use this limit over here and it gives you a real good geometric sense of what the curvature is doing, right? The more the normal vector is changing, right? So the wider spread of normal vectors you have relative to a smaller surface area, if there's a lot of normal vectors for a smaller surface area, that means the surface actually is bending a lot, right? Whereas if you only have like 1 or 2 or 3 or a very, very small number of normal vector directions, right? So maybe like only like this or this or this or this, or really just a small number of directions, that means the surface isn't bending that much at all. It's more or less flat at that point, right? So flatness is a measure of this normal vector on the top here, the cross of these normal vector derivatives being equal to 0, and that gives us sort of a geometric flavor for the analytic notion of curvature. Thank you very much.